Hi guys, welcome to my world of physics infinity. I bring to you another wonderful video on the calculation of the magnetic dipole moment of a sphere that is uniformly charged, and this time it has a volume charge density rho. The sphere is of radius r, mass capital M, charge capital Q, which is uniformly distributed well within its volume, and this is spinning about 1 inch diameter with a high angular frequency omega. I have done videos on the magnetic dipole moment by all the integration process and so on. But here I am going to teach you doing this without integration with a very fascinating concept, introducing the fascinating concept of gyromagnetic ratio. Gyromagnetic ratio is for a body in which the charge and masses are uniformly distributed, then the ratio of the magnetic dipole moment magnitude divided by the magnitude of the angular momentum about the axis is what is called the gyromagnetic ratio, G, and that comes out to be as Q by 2M. We'll see that. And I'm going to use this fascinating concept to evaluate, to work out the magnetic dipole moment of this uniformly charged dielectric sphere. But before I introduce that, let me first of all brief you about the basic concept of the gyromagnetic ratio. Suppose I have a particle of mass capital M having a charge Q, and it is rotating with a uniform angular velocity omega, look from above anticlockwise. Then it has a magnetic dipole moment, and the magnetic dipole moment is QF current times A. Indian Airlines, IA arrow. I, of course, is a scalar, A arrow is a vector, so this comes out to be I is Q times F, area pi r square, and thumb up J cap. This is J cap. So this is the magnetic dipole moment, whose magnitude is, of course, pi would cancel, so omega Q r square by 2. Okay, fine. Now I ask you, what is the angular momentum for this orbital motion? Cool. I omega arrow. I for the particle about the axis is mr square, omega arrow. Omega arrow once again, direction, thumbs up, J cap. So mr square omega J cap. Now, if I divide the magnitude, I have seen some people making that silly mistake of dividing the vector m arrow with L arrow. You don't divide vectors, come on. In physics, you don't have an equation where you divide two vectors. So if you now take the ratio of the magnitude of the dipole, magnetic dipole moment, small m, with the angular momentum, you get a cool answer, Q omega r square by 2 upon mr square omega, and that is what is called the gyromagnetic ratio, and this is Q upon 2m. Now this is we have done for a particle, but mind you, what I'm trying to tell you now, if you have a body which is spinning and the body has a constant charge density as well as a mass density, so a homogeneous mixture of charge and mass, it has a homogeneous mixture of charge and mass, then this gyromagnetic ratio funda can be applicable to any of such bodies, and I can use that now to find the magnetic dipole moment. Okay, let me first of all show you that why I am highlighting this concept. Suppose I think of this sphere, a dielectric sphere of radius capital R having charge capital Q, and the Q is uniformly distributed, and I spin it about this with high angular frequency omega, and I ask you to calculate its magnetic dipole moment. I have done that in my previous lectures in the series of MEC. I have done for disk, I have done for a sphere that was surface charged, so we can do for this. But this integration is going to be very cumbersome. I'll have to break it into elemental disks of, let's say, radius small r, that is r square minus x square under the root, and the disk is from the center x. So break it into elemental disks, find the magnetic dipole moment of each disk, which I have done in MEC 3 in my earlier video, and you can solve that. But this integration, believe me, is going to be real cumbersome. So why don't we use our fascinating gyromagnetic ratio? So easy. I use gyromagnetic ratio, that is Q by 2m, is dipole moment magnitude upon magnitude of angular momentum. So there you are. So m is Q by gyromagnetic ratio multiplied by L. Now what is L? Angular momentum of this solid sphere, I omega, moment of inertia times omega, and moment of inertia, everybody knows, 2 by 5 mr square. So 2 by 5 mr square into omega, I just put the figure, and in one step I get the answer. Magnetic dipole moment is 1 by 5 q r square omega. We have avoided this huge cumbersome integration and done it quickest possible way by the use of the fascinating concept of the gyromagnetic ratio. And believe me that this is applicable to all bodies in which there is a homogeneous mixture of mass and charge, which has a constant volume charge density and a constant mass density. And then if about an axis, if you want to find its dipole moment, then you can use this fascinating. I can even do that for a rod, a uniformly charged rod, whose mass density is also uniform. I can do that for a cylinder, for anything, for anybody. So there you are. I hope this has been a very interesting video for you, and you have learned a very interesting and fascinating concept of the gyromagnetic ratio. Not only that concept, but how to use that in order to solve a very difficult cumbersome integration involving cumbersome integration problem. You like my lectures? Do subscribe my channel and keep on getting these wonderful videos from me. Thank you so much.
If you
Thank
like the video and want me to make more useful videos for you, subscribe my channel and hit the bell icon to stay updated.